Hello, my name is Daniel Evans, and I welcome you to my presentation, Employing and Securing Selective Overclocking in Mobile Applications, based on my extended abstract of the same name. As a quick introduction to myself, I gained my bachelor's in mathematics from Pensacola Christian College back in 2010. I've had 5 years in IT experience between operations, security, and project management. I have been a CISP member since 2018. And currently working on my master's in NYU, working for a MS in cybersecurity. So to break down what I mean by selective overclocking, we will cover a few terms first. We'll discuss hybrid systems, overclocking, and dynamic overclocking, all of which are already well established in the computer industry. We'll go over something fairly new that I call application-specific overclocking, and then my own hypothesis of adding in selective overclocking. We will show you the test, the model that I've developed, and the conclusions that I gained from it, and then talk a little bit about future work. So to start with, what are hybrid systems? The best example available right now is the Nintendo Switch. It is a platform that can switch between a home use, where it connects to a television or monitor and has an outlet power, to being able to be used on the go, where it has dedicated screen, is battery powered. The strengths of these hybrids is that you can use the same applications at home, on a screen, or on the go, but the downside is that you are limited to the power of that handheld system. One way to improve performance on underpowered systems is overclocking. Overclocking is where you increase the clock speed of hardware beyond its rated frequency, the speed at which the manufacturers say is a safe speed. This is often used on older gaming computers in order to allow them to play more modern games and be a little bit more relevant before you move on to buying the next computer. So the pro here is that there's linear increase in performance. Ideally, if you were able to double the clock speed, you would be able to double the number of instructions that component could perform. The cons here is higher power consumption. You will have to increase the voltage to keep up with the higher clock speed. In turn, that means that you'll have more heat, and those components not only could you risk burning them out, but they will age faster from being at higher temperatures longer, shortening their lifespan. And if you go too fast, you will have a much higher chance of errors, where parts of the components will be at different, working different instructions, and it will just get confused or run into errors. So if you're not extremely careful, you'll wind up with a fried computer, much like that egg in the bottom right corner. Moving on to dynamic overclocking. This is exactly what it sounds like. While static overclocking required you to set the clock speeds at boot, dynamic overclocking can be changed anytime after. It is situation dependent, either being changed by the user or by some condition that the computer is looking out for. One example is turbo boost, which is a common name that manufacturers will give for a stable overclock speed that they provide, which the user can enable at any time. It provides more speed, a little bit higher temperatures, but overall doesn't reduce the lifespan of the component much, so those manufacturers are okay with giving it out. There are also programs that reduce clock speed or underclock the system. AMD Power Now will reduce the clock speed and voltage after a period of idleness so that it's saving on power in the long run. This is particularly used on mobile devices, although they do have one for desktops as well. And one more example, which is the closest to what I'll be presenting today, is MSI Afterburner, which is a PC application that allows you to create different profiles, and depending on your situation, you can turn on a profile to give you custom CPU, GPU, and memory clock speeds. If you want to move into high-speed gaming, you can choose the overclocking profile, and if you go back to normal PC work, document work, you can choose a lower profile. Up to now, we've only seen clock speeds change when either the user requests it or when a certain system event occurs. But now we're running into a third kind of overclocking. There are certain Nintendo Switch games that have overclocking built into them. For example, in Legend of Zelda Breath of the Wild, an update added in overclocking. This only occurs on the loading screens, where there is less going on graphically and the CPU has more power available to it. So the CPU jumps from the Switch's rated 1020 MHz to 1786 MHz on the very high side. This caused loading times to drop from around 25 to 50%. Not a small feat at all. Another example is Mortal Kombat 11. In this title, the GPU will increase from the usual rated speed of 307 megahertz to 460 megahertz. This will only occur under certain situations, certain scenarios where the graphics are so intense that the game could drop below that 60 frames per second that they are trying to attain. This is something that the Nintendo Switch had to work out before because it's actually built into the operating system itself. But my question is, why leave it to the operating system to decide what games can be overclocked and which cannot, when there are plenty of third-party titles that could benefit from increasing clock speeds at just the right times? This is what I would call timely overclocking, when the device can be overclocked when the application needs it most, when the scenario calls for it. Certainly, though, not every application can be trusted, which is why the operating system should only do so when it is safe and meets the platform's conservation requirements, whatever the designers decide. This is what I would call selective overclocking. Now, I will note that selective overclocking is not practical for all devices. For gaming systems, there is one primary application, the game, and all other applications, all other background applications are along for the ride. This is not the case for smartphones, where it may not be clear what application is most important to the user, and moving back and forth between different clock speeds with different applications running could cause more thrashing than it would be helpful. To enable selective overclocking, I have created this model of an overclock manager. This is a process that would run inside the operating system. Its functions would be to read the requested speeds from the application, the main application running. Simultaneously, it would calculate the maximum safe speed, depending on the sensor data available to it. Finally, it would take a look at the application's battery credits. This is a concept that would accumulate if the application runs at an underclock speed and would be spent when the application is running at overclock. This concept will allow applications to not abuse the overclock system. But again, the overclock manager takes a look and makes sure that there is sufficient battery credits for the request. Then it sets a new speed and calculates a new credit balance. This can happen at a periodic time, whether it's every second or every fraction of a second. The overclock manager would run through all of these steps. Of this model, we simulated the overclock manager in C++. You can see the full code after the references at the end of this slideshow. The overclock manager first reads the sensor data and requested speeds from a file. These could be separate files, but we decided to make it a single file for simplicity. After that, it calculates the maximum frequency using the sensor data from all of the various sensors. Next, depending on the application's requested speed, it will either request an overclock or request an underclock. These, again, could be the same single function, but we decided to separate these because requesting an underclock is a much simpler calculation than requesting the overclock. Generally, we don't stop an application from underclocking if it chooses to. Next, we will update the state. And this is the point where we set the CPU speed, and we also increase or decrease the battery credits depending on what speed the CPU is currently running in. And at this point, we determine that a period has gone by, and we'll read the next line in the file. Overall, we found our preliminary evidence to be very encouraging. The output frequencies were consistent with our expectations. To be specific, the actual frequency, shown in green here, dropped whenever the maximum safe frequencies, or the requested frequencies, began to fall below it. The frequencies were adjusted every period as intended, and this is something that the platform developer could change as they desire. As shown at the end here, when the battery credits began to reach near zero, this forced the actual frequency to drop down to 1080 megahertz, the rated frequency. Finally, we observed that the battery credit system may do more than just stop overclocking abuse. Rather, the battery credit system encourages application developers to underclock during any slow periods or lulls in their game in order to build battery credit for when they need it most. While this may not increase battery savings in the long run, it does bring application developers into the conversation of when to save battery and provides an overall better experience for the user. So that concludes our experiment, but where do we go from here? First, measure performance gains from simulated and real models figure out exactly how much we're gaining from these, there are online overclocking simulators that we could use to take advantage of that and at least get an idea of what kind of performance gains this provides. Next, include more factors, including maximum battery draw, for example, as a sensor variable. And finally, to develop similar models for selectively overclocking memory and GPU frequencies. It should look about the same, but there could be more sensors and more considerations to include. This concludes my briefing. If you have any questions, feel free to contact me at the information below, and I encourage you to take a look at the references and the actual C++ code below. Thank you.